Chemical properties of the 17th group elements, oxidation states and trends in chemical reactivity. All halogens exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit +1, +3, +5 and +7 oxidation states also, as explained below, where the ns orbital, the ns np orbitals will get excited to go to nd orbitals, as shown here as well. Even the ns orbital electrons will go forward, get excited. This is not 3 electrons but only 1 electron in the s orbital. The higher oxidation states of chlorine, bromine and iodine are realized mainly when halogens are in combination with small and highly electronegative fluorine and oxygen atoms. Example, in interhalogens, oxides and oxyacids, the oxidation states are +4, +6 occur in oxides and oxyacids of chlorine and bromine. The fluorine atom has no d orbitals in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with metals and non-metals to form halides. The reactivity of halogen decreases as we go down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogens. F2 is the strongest oxidizing halogen and it oxidizes other halide ions in solution or even in the solid phase. In general, a halogen oxidizes halide ions of the higher atomic number. Fluorine can oxidize chlorine, bromine, iodine, and chlorine can oxidize bromine and iodine, and bromine can oxidize iodine. The decreasing oxidizing ability of the halogens in the aqueous solution down the group is evident from the standard electrode potential, where iodine has the lowest standard electrode potential, and this is depending of the electrode potential, dissociation enthalpy, electron gain enthalpy, hydration enthalpy. The relative oxidizing power of halogens can further be illustrated by their reactions with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acids. The reaction with iodine with water is non-spontaneous. In fact, iodine can be oxidized by oxygen in acidic medium, just the reverse of reaction observed with fluorine. This is describing the less electronegative nature of iodine. Fluorine H2O gives H plus and fluoride ion. X2, where X can be chlorine and bromine plus water, gives HX and HOX, whereas iodide ion is getting oxidized by water to give iodine gas. I mean not iodine gas but iodine. Anomalous behavior of fluorine. Like other elements of P block in the second group of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity and electrode potentials are all higher for fluorine than expected from the trends set by other halogens. Also, ionic and covalent radii, melting point and boiling point, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, high electronegativity, low FF bond dissociation enthalpy and non-availability of d orbitals in its valence shell. Most of the reactions of fluorine are exothermic due to small and strong bond formed by it with other elements. It forms only one oxyacid while other halogens form a number of oxyacids. Hydrogen fluoride is a liquid with 293 Kelvin boiling point, and due to strong hydrogen bonding, other hydrogen halides are gases. Because of the strong hydrogen bonding of hydrogen fluoride, it is liquid, but other hydrogen halides are not liquid and they are gases. Chemical reactivity towards hydrogen. All the halogens react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. Hydrogen halides dissolve in water to form hydrohalic acids. Some of the properties of hydrogen halides are given in table 7.9. The acidic strength of these hydrogen halides dissolve in water to form acids, and the acidic strength varies in the order. Hydrogen fluoride has the least acidic strength, with hydrogen iodide having the highest. The stability of these halides decreases down the group due to increase in the bond HX bond dissociation enthalpy in the order. The bond dissociation enthalpy of hydrogen and fluorine bond is the highest, where hydrogen and iodine bond dissociation enthalpy is lowest. for iodine, where we see 600 is for hydrogen fluorine bond and 300 for hydrogen iodine bond. Reactivity towards oxygen. Halogens form many oxides with oxygen, but most of them are unstable. Fluorine forms two oxide OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluorides because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to give PuF6, and the reaction is used in removing plutonium as PuF6 from the spent nuclear fuel. Chlorine, bromine, iodine form oxides in which the oxidation states of these halogens range from +1 to +7. A combination of kinetic and thermodynamic factor lead to generally decreasing order of stability formed by halogens, with I having the highest stability, chlorine and bromine having the least stability. With oxides, the higher oxides of halogens tend to be more stable than the lower ones. Chlorine oxides Cl2O, ClO2, Cl2O6 and Cl2O7 are highly reactive oxidizing agents, and these also tend to explode. ClO2 is used as a bleaching agent for paper, pulp and textiles and its water treatment. The bromine oxide Br2, BrO2, BrO3 are the least stable halogen oxides, middle row anomaly, and exist only at low temperatures. They are very powerful oxidizing agents. The iodine oxides I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in estimation of carbon monoxide. Reactivity towards metals. Halogens react with metals to form metal halides. For example, bromine react with magnesium to give magnesium bromide. Reaction with metal, magnesium plus bromine giving magnesium bromide. The ionic character of halides decrease in the order of MF. Metal fluoride having the highest stability, ionic character due to a high electronegativity of fluorine. I think we stopped somewhere in the reactivity with oxygen column, so I will continue from reactivity towards metals. Halogens react with metals to form metal halides. For example, bromine reacts with magnesium to magnesium bromide. Magnesium plus bromine gives magnesium bromide. Ionic character of halide decreases in the order, with metal fluoride having the highest and metal iodide having the lowest ionic character. This is because of the electronegativity of fluorine being the highest. Due to this, the ionic character of the metal fluoride is also the highest. And we also saw that as higher the oxidation state, higher the covalent character. As the oxidation state increases, the covalent character increases. Only at low oxidation state, there will be high chances for oxidation state. And this oxidation character also decreases as we go down the group, with metal iodide having the least, where M is a monovalent metal. Monovalent meaning it is having only +1 oxidation state. If a metal exhibits more than one oxidation state, the halides in higher oxidation state will be more covalent than one lower oxidation state. For example, tin. Okay, I think I read this as well. Yes, I read this as well yesterday. Reactivity of halogens toward other halogens. Halogens combine amongst themselves to form a number of compounds known as interhalogens, a type of XX, XX3, XX5 and XX7, where X is a larger size halogen and X dash is a smaller size halogen. X and X dash, where we can say iodine reacting with chlorine or smaller atoms of fluorine, etc. And this question also I believe I have answered. Yes, I have answered these questions. Okay, let's start with chlorine. The first compound which we are going to study under 17th group. Chlorine meaning Cl2. Chlorine was discovered in 1774 by Scheele by the action of HCl on MnO2. In 1810, Davy established its chemistry nature and suggested that name chlorine on account of its color. Chloros meaning greenish yellow. Chlorine meaning greenish yellow. discovered by Skeel and named by Davy in 1810. Preparation, it can be prepared by any one of the following methods. The first method being heating manganese dioxide with concentrated hydrochloric acid. This is the first. This is also how actually it was actually founded out as well. Magnesium oxide reacting with HCl to give magnesium chloride, chlorine and water. However, a mixture of common salt and concentrated H2SO4 is used in place of HCl. NaCl plus MnO2 plus H2SO4 gives MnCl2 NaHSO4 H2O Cl2. This is also one more method or reaction for chlorine production by the action of HCl on potassium permanganate. KMnO4 plus 16HCl gives potassium chloride, manganese chloride, water and 5Cl2 gas. Manufacture industrial scale process of chlorine is the fourth process we are going to study about. The first being Haber's process, production of ammonia. The second process being Ostwald's process, production of nitric acid. Then the third process is contact process, which is the process of production of sulfuric acid. And it is the fourth process we are going to study about is Deacon's process, which is manufacture of chlorine by oxidation of hydrogen chloride gas by atmospheric oxygen in the presence of CuCl2 acting as a catalyst at 723 Kelvin. HCl plus O2 in presence of CuCl2 gives Cl2 plus water. Electrolytic processes. Second industrial method is electrolytic process. Chlorine is obtained by the electrolysis of brine. Concentrated NaCl solution is called brine. Concentrated or saturated, we can say, solution of NaCl. By electrolysis of the solution, we can obtain chlorine alkali as well, I think. Yes, alkali preparation reaction, which means NaOH preparation reaction. Chlorine is liberated at anode. It is obtained as a byproduct in many chemical industries. Okay, that is a total of 4 processes. 2 processes in the lab with magnesium oxide reacting with 3 processes in the lab with magnesium oxide reacting with HCl give chlorine, and NaCl and MnO4 with in presence of H2SO4 sulfuric acid giving MnCl2 and chlorine. 3 processes with the third process being potassium permanganate reacting with hydrochloric acid to give chlorine, and manufacture is by Deacon's process. The catalyst is CuCl2 cupric chloride and HCl plus O2, basically exposing or oxidation of hydrogen chloride by the atmospheric oxygen in the presence of CuCl2 acting as a catalyst. Properties: it is a greenish yellow gas, that is the reason it was named chlorine by Davy in 1810. Greenish yellow gas with pungent and suffocating odor. It is toxic or poisonous and it has a pungent smell. It is about 2.5 times heavier than the average mass of air. It can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. 239 Kelvin is its boiling point. It's soluble in water. Chlorine reacts with number of metals and non-metals to form chlorides. Al plus 3Cl will give aluminium chloride, and anhydrous aluminium chloride is used as a strong oxidizing strong oxidizing agent. And our common salt, Na plus chlorine will give us our common salt. Iron plus chlorine will give ferric chloride. Phosphorus reacting with chlorine will give PCl3, phosphorus trichloride, which we study the properties of. And S8 plus chlorine will give disulfur dichloride. The oxidation state of sulfur here is +1. It has a great affinity for hydrogen. It reacts with compounds containing hydrogens to form HCl. H2 plus Cl2 gives hydrochloric acid. H2S plus Cl2 will give hydrochloric acid and sulfur. C10H16 plus 8 chlorine will give 16 HCl plus 10 carbon. With excess ammonia, chlorine gives nitrogen and ammonium chloride. With excess ammonia, chlorine gives nitrogen and ammonium chloride, basically describing this reaction. When high amount of NH3 we take, it will react with 3 chlorine to give ammonium chloride and nitrogen gas, dinitrogen gas. Whereas excess chlorine, nitrogen trichloride explosive is formed. When we take ammonia as excess, we will get nitrogen gas and ammonium chloride. And in case of excess chlorine, if we take ammonia plus excess chlorine, then it will give us ammonium trichloride, which is an explosive, and plus H3HCl. With cold and dilute alkalis, chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkalis meaning bases, it gives chlorine and chloride and chlorate. Chloride is formed in both hot and cold solutions of alkali, but hypochlorite is only formed in cold solutions, whereas chlorate is formed in hot solutions. Cold and dilute, less concentration, NaOH plus Cl2 gives salt, NaOCl2 and H2O. In case of hot and concentrated, high reactivity and high concentration, NaOH will react with the chlorine to give 5NaCl, NaClO3. This is a chlorate plus 3H2. Hot and concentrated. With dry slaked lime, it gives bleaching powder. Dry slaked lime is calcium hydroxide. Calcium hydroxide reacting with chlorine to give bleaching powder. The composition of bleaching powder is CaOCl2, CaCl2, CaOH2 dot 2H2O. Chlorine reacts with hydrocarbons and gives substitution products with saturated hydrocarbons and addition products with unsaturated hydrocarbons. For example, they said chlorine react with hydrocarbons, gives substitution products with saturated hydrocarbons. It will basically substitute in place of hydrogen in case of normal saturated hydrocarbons, but in case of alkenes or alkynes which are unsaturated, it will take the double it will not substitute the hydrogen, but it will be added into the compound. In case of methane, this is the chlorination reaction in presence of H mu or sunlight. In case of UV light, chloroform is formed, which is substituting one hydrogen. And in case of ethene, which is C double bond C, as we see here, C2H4Cl2, it actually got added into the compound itself. It did not displace hydrogen as in case of here, but it got added. This is what addition and substitution reactions are. Chlorine water and standing loses its yellow color due to the formation of HCl on HOCl. Hypochlorous acid so formed gives nascent oxygen, which is responsible for oxidizing and bleaching properties of chlorine. Okay, basically when we chlorine dissolving in water, it will decompose if we keep it for some time, and normally chlorine is a yellowish greenish liquid, but in the liquid state, but if we leave it for some time, it will dissociate to give hydrochloric acid and HOCl2, hypochlorous. This hypochlorous, as it decomposes, it will give nascent oxygen. This nascent oxygen has a high oxidizing capacity. Due to that, it acts as a bleaching, it gives the chlorine a bleaching properties. This oxidizes ferrous to ferric, Fe plus 2 to Fe plus 2 to Fe plus 3, which is oxidation, and sulfide to sulfate, SO3 to SO4. Chlorine oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In the presence of water, they form sulfuric acid and iodic acid respectively. The reactions are ferrous sulfate plus H2SO4, which is sulfuric acid, plus chlorine gives iron sulfate, and hydrochloric acid. Sodium sulfate plus chlorine plus water, basically chlorine water reacting with sodium sulfate gives sodium sulfate plus HCl formation. This is sodium sulfite. Sulfite is getting oxidized to sulfate. So a sulfur dioxide gas, chlorine water gives sulfuric acid and HCl. I2 6H2O plus 5Cl gives 2HiO3 and HCl. Iodine getting oxidized from 0 to here, whatever the state it is, maybe +4. It is oxidizing, is a powerful bleaching agent. Bleaching action is due to oxidation. Chlorine plus H2O gives 2HCl plus oxygen. Colored substance plus O, colorless substance. Due to this oxidation, it acts as a strong has a strong bleaching action. Uses: it is used for bleaching wood pulp, required for the manufacture of paper and rayon, bleaching cotton and textiles, the extraction of gold and platinum, manufacture of dyes, drugs and organic compounds such as CCl4, CH3Cl3, CHC chloroform, DDT. DDT is basically dichloro. The full form in chemistry. Yes, diphenyl trichloroethane, where here it contains chlorine. It in CFCs, refrigerants or freons we can call it, etc. In sterilizing drinking water and preparation of poisonous gases such as phosgene, COCl2. COCl2 is called phosgene and it is a poisonous gas. And tear gas, CCl3NO2, mustard gas of this one. Okay, example question: write the balanced chemical equation for the reaction of Cl2 with hot and concentrated NOH. Is the reaction a disproportionation reaction? Justify. Okay, the reaction is basically given here. With hot, basically it is same as the, except for the chlorate and hypochlorite differences, wherein cold and dilute it formed a hypochlorite. In hot and concentrated it will form a chlorate, NaClO3. Here the oxidation state, if we see, of Cl2 it is 0, NaCl it is -1, NaClO3 it should be +1 -6, so it should be around +5. In sodium chlorate, the oxidation state of chlorine is, it is a +5. Yeah, it is +5. So it is indeed a disproportionation reaction where chlorine will have a -1 in case of NaCl and +5 in case of NaClO3. So yes, Cl2 plus 6NOH plus gives 5 NaCl, NaClO3 and H2O. Yes, chlorine from 0 oxidation state is changed to -1 and +5 oxidation state. Give the reason for bleaching action of Cl2. Still water, when we leave chlorine in still water, it loses its yellow color because of formation of hydrochloric acid and HOCl or something like that. It is, yes, HOCl. HOCl, this HOCl can give out nascent oxygen, which will which can easily oxidize, which acts as a strong oxidizing agent. And this is the same case which we saw in case of ozone layer. Ozone O3 can give out nascent oxygen and act as a strong oxidizing agent. In the same way, chlorine also act as a, not chlorine but HOCl, giving out nascent oxygen, also acts as a strong oxidizing agent. And because of this oxidizing property, it also gains a bleaching property or bleaching action. Name two poisonous gas which can be prepared from chlorine. Phosgene, which we saw in the uses, phosgene COCl2 is poisonous gas, and chlorine itself is actually a toxic suffocating gas. As for more, we can say even tear gas is produced, and chlorine, phosgene, and poisonous gases prepared via Cl2R. Phosgene, yes. Chloropicrin. Okay, mustard gas also is a poisonous gas. Its use is a chemical warfare agent. And phosgene was used as a chemical weapon in World War I. And chloropicrin, it is also like as a tear gas. In mustard gas also is a chemical warfare agent. Chlorine itself, as I said before. Now, hydrogen chloride or hydrochloric acid. It bleaches vegetable or organic matter in the presence of moisture. Bleaching effect of chlorine is permanent. Glauber prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davy in 1810 showed that it is a compound of hydrogen and chlorine. Davy also gave the name for chlorine, saying it is yellow color, and he also proved that it is a HCl is a product of hydrogen and chlorine in 1810 itself. And the reaction, Glauber prepared this by heating NaCl plus H2SO4 gives NaSO4, Na2SO4 plus HCl. Glauber prepared it. Davy named it. As for finding chlorine itself, Skley found it, or SC, leave it be. Okay, preparation of hydrochloric acid. In laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. And this is basically the method Glauber used. NaHSO4 plus HCl, NaHSO4 plus NCl again if we heat. With this NaHSO4 again if we heat with NaCl, we will get Na2SO4 plus HCl. HCl gas can be dried by passing through concentrated sulfuric acid. Because H2SO4 is a strong dehydrating agent. Properties: it is a colorless, pungent smelling gas. It is easily liquefied to a colorless liquid. Boiling point is around 189 Kelvin and freezes to a white crystalline solid. Freezing point is 159 Kelvin. It is extremely soluble in water and ionizes as follows. HCl plus H2O gives hydronium ion and chloride ion, which has a Ka value of 10 power 7, which is also incredibly high. And when this incredibly high value of Ka Ka, dissociation constant, we saw even in case of the first step reaction for sulfuric acid, which was close to reaching infinity. Here as well it is not reaching infinity, but it is 10 power 7, which normally dissociation values, we saw the second step dissociation for sulfuric acid was around 10 power minus 2 into 10 power minus 2, and compared to such minute value 10 power minus 7 is very high, but the first step is very high compared to chlorine in case of hydrochloric acid, I mean sulfuric acid. Its aqueous solution is called hydrochloric acid. High value of dissociation constant Ka indicates that it is a strong acid in water. It reacts with ammonia and gives white fumes of ammonium chloride. When 3 parts of concentrated HCl and 1 part of concentrated HNO3 are mixed, okay, so 3 by 4 of HCl and 1 by 4 of nitric acid is mixed, aqua regia is formed, which is used for dissolving noble metals, example gold and platinum. 3 by 4 of HCl, 1 by 4 of HNO3. Yes, if this is mixed, this is a stoichiometric ratio, and if this is mixed, we will get aqua regia, dissolving gold, noble metals like platinum, etc. It is, I don't think it is the first time for us hearing the name aqua regia, and it is formed which is used to dissolving noble metals, example gold, platinum. Gold plus 4H plus and the nitrate ion plus 4HCl gives AuCl4 ion, anion, no, salt I believe, plus NO and water. Platinum 16H plus, 4NO3 minus, 18Cl minus, 3 platinum Cl6 2 minus, 4NO and 8H2O. It seems platinum requires more aqua regia as compared to gold, so you can say gold dissolves more easily in aqua regia than platinum, I think at least. Hydrochloric acid decomposes salts of weaker acids. Example, hydrochloric acid decomposes salts of weaker acids. Example, carbonates, hydrogen carbonates, sulfides, etc. It decomposes directly, it doesn't dissolve, but directly decomposes salts of weaker acid. Example, sodium carbonate, which is a weaker salt acid, with HCl will give NaCl, H2O and CO2. NaCH3, this also decompose in HCl to give NaCl, H2O and CO2. Exactly same reaction. And Na2SO3 plus 2HCl gives 2NaCl, H2O and SO2. Just what change is sulfur. In place of carbon dioxide, there is sulfur dioxide. The uses of hydrochloric acid, it is used in the manufacture of chlorine, NH4Cl, glucose and glucose from cornstarch. It is used in manufacture of chlorine. Okay, we saw the manufacture of chlorine was exposing HCl to oxygen, which was the one of the Deacon's process, and one more was the second industrial process was electrolytic process. Okay, this doesn't contain HCl. For extracting the second, first is manufacture of chlorine through Deacon's process, industrial method, and NH4Cl, ammonium chloride, formation or production of ammonium chloride and glucose. And glucose we produce through or from cornstarch. For the second use is for extracting the glue from bones and purifying bone black. Okay, whatever that means. In third, in medicine as a laboratory reagent. Medicine, it is used as a laboratory reagent, and one more use it is naturally as stomach acid. Stomach acid is HCl itself. It is not produced or artificial, but our stomach acid is HCl, which everyone knows. And even though it seems that the uses of comparing HCl and H2SO4, the uses of HCl are comparatively less than H2SO4. Maybe because the H2SO4 first step reaction has a very higher dissociation constant, which is reaching infinity, even though the hydrochloric acid also has the very high dissociation constant, but maybe because of that reason, and being H2SO4 being diprotic, it is used more commonly, and it also gave that the more the sulfuric acid produced, the more the indicating the strength of the nation's industrial strength. And the example question: when HCl reacts with finely powdered iron, reaction with iron, okay, it forms ferrous chloride and not ferric chloride. It forms FeCl, FeCl2 and not FeCl3. Why? In reaction with iron produces H2. Fe plus 2HCl gives FeCl2 plus H2. Liberation of hydrogen prevents the formation of ferric chloride. So basically, I think hydrogen is taking the electrons, and because of that, no. I think it's something like that. And next topic is oxoacids of halogen, which they gave only about a half a page when compared to nitrogen. This is actually very less, where it gave 3 or 4, 5 or 6 pages, or 3 or 4 pages. Oxoacids of halogens, due to high electronegativity and small size, fluorine forms only one oxoacid, HOF, known as fluoric 1 acid or hypofluorous acid. Fluoric 1 acid or hypofluorous acid. The other halogens form several oxoacids. Most of them cannot be isolated in a pure state. They are very stable only in aqueous solutions or in the form of their salt. This exact same lines we saw in case of oxoacids of chalcogens as well, where exact same lines here are repeated here. Most of them cannot be isolated in pure state. They are stable only in aqueous solutions or in the form of their salts. Now let's continue. The oxoacids of halogen are given in table 7.10 and their structures are given in figure 7.8. Let's see the table as well as the diagram. Oxoacids of halogens. Halic acid 1, this is the only oxoacid of fluorine, and this is the hypochlorous acid or chloric acid, hypobromous acid or bromic acid, hypoiodous acid or iodic acid. These are the basically oxoacids of halogens. And as for halic 3 acid, fluorine doesn't form halic 3 acids, and only chlorine is the only one that can form a halic 3 acid, which is chlorous acid. We call it as chlorous acid. Okay, chloric acid actually different from hypochlorous acid, and here bromic, chloric and iodic acids are different from hypoiodous, hypobromous and hypochloric acid. Because hypofluorous acid is the only oxoacid of fluorine, maybe that is the reason it is both called hypofluorous acid as well as the fluoric acid. Okay, and halic 3 acid is only formed by chlorine, which is called the chlorous acid, and halic 5 acid with +5 oxidation state. All the three except fluorine form them with chloric acid, bromic acid, iodic acid. And halic 7 acids, which is called as perhalic acid. Perhalic acid is formed by all the three except fluorine, and it is called perchloric acid, perbromic acid and periodic acid, which seems like periodic acid, but I think it is pronounced as periodic acid. Now the structures of oxoacids of chlorine. Hypochlorous acid, HOCl, which is the one that is releasing nascent oxygen when chlorine is placed in water or is in still water. This is the one releasing the oxygen and nascent oxygen and gives the high bleaching capacity of chlorine water. And this is the chlorous acid, with chlorine having a +3 oxidation state due to having this oxygen has -2, -1, so +3. Here it is -1, so +1 oxidation state in case of hypochlorous acid. The only acid formed by all 4 of the halogens is hypochlorous acid. In case of chloric acid, -2, -2, -1, so +5 oxidation state for chlorine. Perchloric acid, -2, -2, -2, -1, so total of +7 for chlorine. Now the next type of compounds seen are interhalogen compounds. When two different halogens, and this condition is that the main atom, which is the structure, is basically X and X dash. Basically this X dash has to be the smaller atom, small compared to X atom. When two different halogens react with each other, interhalogen compounds are formed. They can be assigned general compositions as XX dash, XX dash tri, X penta X dash, X hepta X dash, where X is a halogen of larger size, and X dash of smaller size, and X is more electropositive than X dash. We can take an example of iodine, which is larger, more electropositive, and smaller one we can take chlorine or fluorine. Maybe we can even take bromine as well. The ratio between radio of X and X dash increases, number of atoms per molecule also increases. The ratio, like if this is a very large molecule, I mean atom, compared to the X dash, the more the number of X dash it can bear. If they are of the same size or a less significant change in size, then that means less the number of atoms the larger atom can accept. Thus, iodine 7 fluoride should have the maximum number of atoms, as the ratio of radii between I and F should be maximum, and along with the electropositivity of iodine having the highest, or we can say electronegativity is the least. That is why its formula is IF7, having maximum number of 7 fluorine atoms. Preparation: the interhalogen compounds can be prepared by the direct combination or by action of halogen on lower interhalogen compounds. Action of halogen on lower interhalogen compounds. Okay, these interhalogen can be prepared direct combination of the halogens, like if in case of this reaction where chlorine, actually let's continue read. The product formed depends upon some specific condition. For example, this is a direct addition combination method where Cl2F2, the size is not much different. There is difference, but as there is only one group difference, the size difference is a little less compared to chlorine. If we compare fluorine and chlorine, and fluorine and iodine and fluorine have the highest size difference, and because of that only ClF is possible. When ClF is formed here, but when in comparatively less temperature as compared to here, Cl2 plus 3F2, which is excess amount of fluorine if we take, and Cl2 we react, we will get ClF3. Cl, which is the X-3 compound, and iodine and chlorine, when we have equal volume or equimolar, we will get ICl. When we take chlorine to be excess, we will get ICl3. Bromine and fluorine, when bromine is diluted with water, we will get BrF3, and when we take excess of fluorine, we will get BrF5. Some properties of interhalogen compounds are given below. Type XX-1, chlorine fluoride, bromine fluoride, iodine fluoride, bromine chloride, iodine chloride. Chlorine fluoride is colorless gas, bromine fluoride is pale brown gas, bromine itself is brown in color, and when we add fluorine to it, it will lightly lose its color, becoming pale brown in gas. And iodofluoride detected means there is no color in the our visible spectrum, I guess. ICl, ruby red solid alpha form, brown red solid beta form. It can be red, which can be ruby red in case of alpha form, and in case of beta form it is brown red. Both are solids, not gases. The above three are gases, but the iodochlorine compound is not gas but solid. And iodobromine is brown in color, and in case of chlorine trifluoride, it is colorless gas. Bromo trifluoride, yellow green liquid. Iodo trifluoride, yellow powder. Iodo trichloride, it is orange solid. Iodopentafluoride, colorless gas but solid below 77 Kelvin. Bromine pentachloride, colorless liquid. Here the shapes are bent T, meaning it's like a bent shaped, like a disordered T shape. And in case of pentamolecules, they are square pyramidal, or a square pyramidal, except IF7, which is possible. It is a colorless gas, and it is pentagonal bipyramidal. ClFi, it is colorless liquid. BrFi is also colorless liquid. They are giving ICl3, which is solid which is only pure solid, and it actually dimerizes as chlorine bridge. These are all covalent molecules and are diamagnetic in nature. They are all volatile solids or liquid at 298 Kelvin, except chlorine fluoride, which is a gas. Their physical properties are intermediate between those of constituent halogens, except that of their melting and boiling points are little higher than expected. Their physical properties are similar to individual halogens, but their melting and boiling points are little higher, maybe due to increase in their mass. As more number of atoms join together, their atomic mass increases, and as the mass increases, the boiling point also increases. Their chemical reactions can be compared with individual halogens. They have similar chemical reactions as compared to halogens. In general, interhalogen compounds are more reactive than halogens, except fluorine, because of maybe due to instability. This is because X bond X dash in interhalogen is weaker than XX bond in halogens, except fluorine. All these undergo hydrolysis, giving halide ion derived from the smaller halogen and a hypohalite. When XX dash halite, when XX dash 3 halate, and when XX dash 5 upper halate, and when XX, these are basically the oxoacids. Oxoacids we saw here, the perhalate, halic, halus. Anions derived from the larger halogen. XX dash plus water gives HX dash plus HOX. This is a, what is this? This is the hypohalite. Their molecular structures are very interesting, which can be explained on the basis of valence shell electron repulsion theory, electron pair repulsion theory. The XX3 compound have the bent T-shaped, XX5 compounds are square pyramidal, and IF3 has a pentagonal bipyramidal structure. Totally, there are three kind of structures seen here. The first one being a disordered or a bent T-shape, the second one being a square pyramidal structure, and the third one a single structure seen only in iodine heptafluoride, which has a pentagonal bipyramidal structure. Discuss the molecular shape of bromine trifluoride on the basis of VSEPR theory. This is, as we see here, it is somewhat a bent T shape, and there are two lone pairs here. Normally the T is like this, but it is bent here in this case. The central atom is bromine. They are discussing here, they are telling us why the reason. The central atom of bromine has 7 electrons in the valence shell. This is normal in all the halogens. 3 of these electrons will form electron pair bonds with 3 fluorine atoms, leaving behind 4 electrons. Basically, total 7 electrons are there. 2 lone pairs will be left out, and 3 of the electrons from these 7 will form covalent bonds with these 3 fluorine atoms. Thus, there are 3 bond pairs and 2 lone pairs. According to VSEPR theory, this will occupy the corners of a trigonal bipyramidal. The 2 lone pairs will occupy the equatorial positions to minimize lone pair, and the bond pair lone pair repulsion, which are greater than the bond pair repulsions. In addition, the axial fluorine atoms will be bent towards the equatorial fluorine in order to minimize the lone pair repulsions. The shape would be that of slightly bent T shape. They are basically saying that basically using a principle lone pair repulsions greater than lone pair bond pair repulsions greater than bond pair repulsions. And using this principle, they basically define this bent T shape of the or disordered T shape of the XX-3 interhalogens or interhalides. These compounds can be used as a non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents. ClF3 and BrF3 are used for production of UF6 in the enrichment of 235U. Uranium plus chlorine trifluoride will give us urine hexafluoride plus chlorine fluoride gas. In text question, why is iodochlorine more reactive than iodine? Maybe it's because of the instability of the interhalogen compounds, and as iodine bond is more stable than ICl, maybe due to that reason ICl is more reactive than I2. And we can even say the ICl bond dissociation is, we can maybe think that it is lesser than the bond dissociation enthalpy of I2. Maybe that can also be one of the reasons. And with this we completed the 17th group elements. Let's directly go to the 18th group, the final group which we are going to study about in the P block elements. The group 18 noble elements. We have 6 elements here which we will see in the periodic table. We are going to study about in the 18th group are helium, neon, argon, krypton, xenon, radon, and the last one being oganesson, which we are not going to study about. There are a total of 6 elements of helium, neon, argon, krypton, xenon and radon. All these are non-metals. We studied about from the pnictogens, which is the 15th group, which contains nitrogen, phosphorus, arsenic, antimony and bismuth with 2 non-metals, 2 alkaloids and 1 metal. whereas in the oxygens group, or the chalcogens 16th group or the chalcogen family, we have oxygen, sulfur, selenium, tellurium, and polonium. We there is also livermorium, but we didn't study about the last period, and mostly about oxygen and sulfur. We only studied mostly about oxygen and sulfur. And the 17th group is fluorine, chlorine, bromine, iodine, and astatine, which are all non-metals, except in case of okay, yes, all are non-metals, all are halogens, and all are more reactive, high reactive. And we studied mostly about the first four: fluorine, chlorine, bromine, and iodine. And now the 18th group of the noble gases, we are going to study about helium, neon, argon, krypton, xenon, radon. Group 18 consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. All these are gases and chemically unreactive. They form very few compounds. Because of this, they are termed as noble gases. Basically, they have a complete octet or a complete configuration, electronic configuration. Because of that, they are very unreactive. That is why we call it as inert elements or noble elements. And this noble configuration is what gave them to be a part of this group 18 elements. Occurrence: all the noble gases except radon occur in the atmosphere. All these noble gases, as they are inert, occur in the atmosphere, but radon doesn't appear in the atmosphere. Maybe it's radioactive. The atmospheric abundance in dry air is 1% by volume, of which argon is the major constituent. All the noble gases, if we see the atmospheric abundance is by 1%, that is not including moisture or water content, as they said, specifically mentioned that it is in dry air. And out of this 1% of noble gases in the atmosphere, argon constitutes the major component. Helium and sometimes neon are found in minerals of radioactive origin. Example: pitch blende, monazite, cleveite. Helium and neon are found in radioactive minerals or minerals of radioactive origin, which can be pitch blende, monazite, cleveite, etc. The main commercial source of helium is natural gas. Natural gas. Okay. I didn't get what you mean by natural gas. The main source, commercial source, is natural gas. What is natural gas? Natural gas is fossil fuel and acid occurring mixture found deep. Okay. Natural gas is a fossil fuel and naturally occurring mixture of hydrocarbon gases found deep underground, often near oil fields. This is colorless, odorless, and odor is added later for safety and highly flammable. Natural gas, naturally occurring mixture of hydrocarbon gases found deep underground, often near oil fields. It is colorless, odorless, and highly flammable. Main components of natural gas: methane 70 to 90%, ethane, propane, butane, and there are small amounts of carbon dioxide, hydrogen sulfide, nitrogen, and helium in some gas field. Why is helium found in natural gas? Helium is produced by the radioactive decay of elements like the alpha decay. Alpha decay produces helium. Heavy elements like uranium and thorium in the Earth's crust. It accumulates in natural gas reservoirs over millions of years. Some natural gas fields, especially in USA, Qatar, and Algeria, are rich in helium up to 7% in rare cases. Normally we saw there is some amount of helium, but mainly constituted of 70 to 90% is methane. But even in some fields of some gas fields, up to 7% there are helium cases, helium extraction done by cryogenic distillation of natural gas after removing methane separated. Okay. The main commercial source of helium is natural gas, xenon, radon, and rarest element of the group. Xenon and radon are the rarest elements of the group. We saw the occurrence was in the atmosphere, which was around dry atmosphere by volume. If we take, it is around 1%, and 1% of which argon is the highest volume, and neon and helium are found in minerals of radioactive origin, and the main source of helium is natural gas. Xenon and radon are the rarest elements of the 18th group. Radon is obtained by the decay product of, that is 226Ra. What is that? Ra, it is, yes, radium. It is a decay of 226 radium gives radon. When 226 radium decays, it will give radon plus an alpha particle. This is the alpha decay of radium. Maybe it is because it is obtained from radium, they gave it a name of radon. Example: why are the elements of group 18 known as noble gases? Because they have a full electronic configuration and they do not react. They are called as noble or inert gases. The elements present in the group 18 have their valence shell orbitals completely filled, and therefore they react with a very few elements only in certain conditions. Therefore they are known as noble gases. The important atomic and physical properties of group 18 elements along with their electronic configuration are given in table 7.2. The trends in their atomic, physical, and chemical properties of the group are discussed here. Atomic and physical properties of group 18 elements. Helium is 2. Atomic number of helium is 2. Neon is 10. Argon is 18. Krypton is 36. Xenon is 54. And radon is 86. Atomic mass: helium is 4. Neon is 20. Argon is 40 approximately. Krypton is 84. Xenon is 131. Radon is 222. All the electronic configurations are completely filled. Only helium, we see that it does not have a p subshell. Even though it doesn't have a p subshell, we placed it under the p block elements because it has characteristics of the noble gases. Normally it has an S configuration, so it should be placed in S block, but we placed it in P block because its chemical properties, physical properties, everything are similar to noble gases, the 18th group, or more, we can even say it is related to the P block elements. Because of that, we placed helium on the top of the 18th group here. And as for comparing atomic radius increases as we go down the group, with helium having 120 and neon having 160, argon having 190 and krypton having 200, xenon 220. Radon, they did not give the atomic radius. The ionization enthalpy is really high, where the comparison, if we do, nitrogen had a ionization enthalpy of 1400 kilojoule per mole, and when we compare oxygen had a ionization enthalpy of 1300 approximately, and fluorine had a ionization enthalpy of 1600 or 1700 approximately. But helium, if we see, it is 2400 approximately, and all are above 1000, and neon has 2000, argon has 1500, krypton has 1400, xenon has 1170, and radon has 1037. This is as expected. It decreases as we go down the group. As for electron gain enthalpy, all are positive electron gain enthalpy, as because we are disturbing the configuration by giving them an electron. Because of that, the electron gain enthalpy is positive. We should give energy for them to take electron. We are disturbing the stability here. Because of that, we need to add more energy. And neon has the highest electron gain enthalpy, whereas this is not negative enthalpy, this is positive electron gain enthalpy, with neon having the highest positive electron gain enthalpy and helium having the lowest electron gain enthalpy. As for density, the density increases as we go down the group. This is common as well because increases in mass. And melting point, helium they did not give a melting point, and neon it is 24 Kelvin, argon 84, krypton 115, xenon it is 161, and radon it is 202, which are significantly lower melting points. And boiling points for helium is 4.2, neon it is 27. All are within the 200 range. The atmospheric content is very less. It is around, in case of parts per million, helium is around 500 parts per million, and argon is around 1800 parts per million, krypton is 0.93, and xenon it is 114 parts per million. Radon is 8.7 parts per million, which is very less. And the basic properties, electronic configuration. All the noble gases have general electronic configuration of Ns2 np6, except helium, which has 1s2. Many of the properties of noble gases include their inactive nature and are ascribed to their closed shell structures. Ionization enthalpy, due to stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radius increases down the group as it should with increase in atomic number. Electron gain enthalpy, since noble gases have stable electronic configuration, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpy, with neon having the highest. Physical properties, all the noble gases are monoatomic. They are colorless, meaning they do not form monoatomic, meaning helium doesn't exist as He2, He3 or He4. It only exists as He. They are colorless, odorless and tasteless. They are sparingly soluble in water. They have very low melting and boiling points because the only type of intraatomic interaction with these elements is weak dispersion forces. If there is no bonding, there is no attraction, there is no forces between the molecules, or not molecules but atoms. Because of such a reason, their melting boiling points are very low. Helium has the lowest boiling point, which is 4.2 Kelvin of any known substance. It has an unusual property of diffusing through the most commonly used laboratory materials such as rubber, glass or plastic. As diffusing through most, it seems it is passing through maybe. Example, noble gases have very low boiling points. Why? Noble gases, being monoatomic, have no interaction forces except weak dispersion forces, and therefore they are liquefied at very low temperatures, hence they have low boiling points. Helium having the lowest boiling point. Chemical properties of the 18 group elements. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to the following reasons. worst reason, noble gases except helium have a completely filled NS2 and NP6 configuration, and helium also has a completely filled uh, doublet configuration, which is doublet, I believe, yes, 1s2 in the name. Electronic configuration in their valence shell, they have high ionization enthalpy and more positive electron gain enthalpy. They don't want to be disturbed by gaining electrons. The reactivity of noble gases has been investigated occasionally ever since their discovery, but all attempts to force them to react from their compounds were unsuccessful for quite a few years. Okay, to form compounds before were unsuccessful, but in March 1962, Neil Armstrong, which is similar name, 1962, then at University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2 plus PtF6. He then realized that the first ionization enthalpy of molecular oxygen is very high, 1000, was almost identical with that of xenon, which is also 1170, a little lower than actually oxygen. He made the efforts to prepare same type of compound with xenon and was successful in preparing another red color compound, Ze plus PtF6 minus, by mixing platinum fluoride, hexafluoride and xenon. After this discovery, a number of xenon compounds, mainly with electronegative elements like fluorine and oxygen, have been synthesized. Basically, Neil Bartlett in the University of British Columbia observed the first noble gas reaction. Basically, observed that oxygen and xenon have similar ionization enthalpies, and oxygen was forming a complex with platinum hexafluoride, and similar way, because they have same ionization enthalpy or similar ionization enthalpy, he thought maybe even xenon can form a similar compound. Because of that, he tried and he was successful in making xenon react and form the same exact compound, which gave the same red color. And after this discovery, many of the compounds with xenon were formed. The compounds of krypton are fewer because xenon has the highest electronegativity. Xenon, as if we see in the table, has the least ionization enthalpy. It is the lowest group element, not including radon. It has the least ionization enthalpy. Because of that, xenon is the most, we can say it is one of the most reactive noble elements. The compounds of krypton are fewer. Only the difluoride, krypton difluoride, has been studied in detail. Compounds of radon have not been isolated but only identified. Radon fluoride by radio tracer technique. No true compounds of argon, neon or helium are yet known. Basically, they are saying that we have studied many compounds of xenon and there are very less compounds of krypton, and we only studied detail about krypton fluoride, difluoride. And as for compounds of radon, they have been traced. We know that they exist, compounds of radon exist, but we did not isolate them, we did not separate them and study them. This tracing technique is the radio tracer technique, and no true compounds of argon, neon or helium are yet known. True compounds are not yet found or don't exist in normal condition. Xenon fluorine compounds, and this xenon, it forms compounds with oxygen and fluorine because of their electronegativity. Xenon forms 3 binary fluorides, XCF2, XCF4 and XCF6 by the direct reaction of the elements under appropriate experimental conditions. Xenon gas plus fluorine Xenon, we take it in excess at 673 Kelvin, very high temperature, and 1 bar of pressure. XeF2 is taken. And in 1:5 ratio of fluorine is taken in excess of xenon plus fluorine. We get 873 Kelvin at really high pressure. We get xenon tetrafluoride. And in case of 1:20 ratio, I think it is 1:20 being fluorine in excess. Yes, for 1 xenon we take 20 fluorine. In such a case, at which is a little lower temperature, not little, more lower temperature compared to the tetrafluoride, but 10 times the pressure. In such a case, we will get xenon hexafluoride. Xenon hexafluoride can also be prepared by the interaction of xenon tetrafluoride and oxygen dioxygen difluoride at 143 Kelvin. Xenon tetrafluoride plus O2F2 gives XeF2 plus O2. XeF2 plus XeF4 and XeF6 are all these three compounds of xenon fluorides. These are colorless, crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They can easily release fluorine. They are readily hydrolyzed even by traces of water. For example, xenon difluoride is hydrolyzed to give xenon, hydrogen fluoride and oxygen. Xenon fluoride plus water will give xenon, hydrogen fluoride and oxygen. The structure of the three xenon fluorides can be deduced from valence shell electron pair repulsion theory and are shown in figure 7.9 XeF2. Basically the structures are given here. 7.9. A is the structure of XeF2, a linear structure, but xenon has total of 4, yes, a total of 8 electrons, so 4 lone pairs, and with 1 lone pair used in bonding, 3 lone pairs are there. This forms a tetrahedral geometry and a linear shape. As for B is XeF4 xenon tetrafluoride. In this case, it uses 3 lone pairs for bonding. No, not 3 lone pairs. It uses 2 lone pairs for bonding to form 4 covalent bonds, and it gives us a square planar structure. And C is xenon hexafluoride, which uses 3 lone pairs for bonding, and there is a single lone pair. And due to the more lone pair bond pair repulsion compared to bond pair repulsion, we will get a disordered octahedral here in case of xenon hexafluoride. And D is xenon XeOF4. In here, oxygen is forming a double bond. Here as well, xenon has a +6 oxidation state, meaning total of 6 electrons were used. Only 1 pair is remaining, and here it is a square pyramidal structure, trigonal bipyramidal geometry. No, not trigonal bipyramidal. It is octahedral geometry and square pyramidal shape. And in case of XeO3, it is a pyramidal shape with 1 lone pair being struck. It is a tetrahedral geometry and pyramidal shape like NH3 molecule. I think that is a structure. XeF2 and XeF4 have linear and square planar structures respectively. XeF6 has 7 electron pairs, 6 bonding pairs and 1 lone pair, and would thus have a disordered octahedral structure as found experimentally in the gas phase. Xenon fluoride react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. XCF2 plus phosphorus fluoride will give XCF plus cation, and PF6 minus anion, or XCF4 plus antimony pentafluoride will give a similar anion and cation of the xenon and anion. Let's read the statement. Xenon fluorides react with fluoride ion acceptors, basically fluoride ion acceptors, basically accepting electrons, to form cationic. When it's giving electrons, it will form a plus charge. This plus charge is called cationic species. And in case of metal fluoride, this is in case of non-metals with phosphorus and antimony fluorides. In case of metal fluoride, it will form metal plus and anionic complexes. In case this metal can be sodium, potassium, rubidium or cesium, which is the alkali metals. Xenon oxygen compounds. Hydrolysis of XCF4 and XCF6 with water gives xenon oxide, trioxide. This is not a 0, this is an O. 6XEF4 plus 12H2O gives 4Xe plus XCO3 plus 24HF and 3 oxygen. Normally we saw these compounds normally dissociate or decompose in water, where the reaction was in water XCF2 completely becoming XCHF and O2, but here when we be in excess amount of water or so, it gives xenon oxygen compounds as well. And in case of this is in case of tetrafluoride, this is in case of hexafluoride, where it reacts with water to give XCO3 and HF. Both are XCO3. Partial hydrolysis of XCF6 hexafluoride gives oxyfluoride, XCOF4 and XCO2F2. Complete hydrolysis, we will get complete xenon oxygen compounds, but when partial hydrolysis takes place, we will get xenon, oxygen and fluorine compounds, oxyfluoride compounds. XCF6 plus H2O gives XCOF4, XCF6 plus H2O gives XCO2F2 plus 4HF. HEO3 is a colorless explosive solid and has a pyramidal molecular structure. We saw many explosives in this chapter, where the first one was phosphine, the second one was, I think it was I don't remember. Phosphine, I'll see that later, I guess. And now itself, somewhere in the halogens, we saw an explosive. I used, okay, for netting agents and fine. And XCO4 is a colorless volatile liquid and has a square pyramidal molecule structure. XCO3 is colorless explosive solid, has a pyramidal molecular structure. And uses of the noble gases: helium is a non-inflammable and light gas, hence it is used in filling balloons for meteorological observations. It is also used in gas-cooled nuclear reactors. Liquid helium, which has a boiling point of 4.2, finds use as a cryogenic agent for carrying out various experiments at low temperatures. It is used to produce and sustain powerful superconducting magnets. Superconductors can exist in extremely low temperature. Because of this low temperature, maybe superconducting magnets, which form essential part of modern NMR spectrometers and magnetic resonance imaging MRI systems for clinical diagnosis. It is used as a diluent diluent for oxygen in modern diving apparatus because of its very low solubility in blood. Neon is used in discharge tubes and fluorescent bulbs for advertisement display purposes. Neon, we see various colorful lights, and this is for advertisement purposes. Neon bulbs are used in botanical gardens and in greenhouses. Argon is used mainly to provide an inert atmosphere in high temperature metallurgical processes, welding of metals or alloys, and for filling electric bulbs. It is also used in laboratory for handling substances that are air sensitive. There are no significant uses for xenon or krypton. They are used in light bulbs designed for special purposes. In text question, why is helium used in diving apparatus? We saw this in our solutions chapter, where when we dive with normal oxygen at lower temperature where pressure is directly where solubility is directly proportional to pressure in gases. As we go lower in the diving as we dive deeper into the sea, the higher the pressure increases on us, and due to that the nitrogen in the air we breathe will dissolve more into our blood, and this nitrogen, as it dissolves, it forms bubbles or obstructions or hindrances in our blood system, which will lead to a disease of a disorder, or we can say a disorder of bends. Because of such a reason, to reduce the dissolving of nitrogen in our blood, we use helium to reduce the partial pressure of nitrogen. Its solubility depends on the pressure, external pressure, as well as the individual partial pressure as well. KH, yes, Henry's constant, depends on the pressure and the mole fraction in the solutions chapter. That is to reduce the partial pressure of nitrogen, we use helium. And because helium is also less dissolving in it dissolves less, they gave in the uses part where they said it used as a diluent for oxygen in modern diving apparatus because it has very low solubility in blood. Balance the following equations: XeF6 plus H2O, XeO2F2 plus HF. Okay, 2 here, 2F, and as for oxygen, I think this is not 2. This is not 2. Here first for oxygen, let's balance oxygen first, or let's try to balance fluorine first. No, it's oxygen is better, I think. Oxygen, 2 oxygen, 4 fluorine. I think it is balanced. Two here, 4 here. Where oxygen, xenon, there is 1 xenon on the both sides. Fluorine, there are 6 fluorine, F6, and here it is 4 plus 2, it is 6, so fluorine is balanced. As for H2O, there are 4 hydrogens on the left hand side and there are 4 hydrogens on the right hand side. There are 2 oxygens on the left hand side, there are 2 oxygens on the right hand side. The equation is balanced. Why has it been difficult to study the chemistry of a radon? Maybe it's because it's a radioactive element and it does not exist completely. They gave it as the radioactive element of radium, which decomposes, which alpha decays to give radon, and maybe due to having low half-life or maybe due to that reasons. And we basically completed the chapter, but let's read a summary as well, which is around 1 page. Summary. Group 13 to 18 of the periodic table consists of the p block elements with their Valence electronic configuration NS2 and P1 to 6. Group 13 and 14 were dealt with in class 11. In this unit, remaining groups of p block element have been discussed. Group 15 consists of 5 elements, namely N, nitrogen, phosphorus, arsenic, antimony, and bismuth, which have general electronic configuration of NS2 and P3. Nitrogen differs from other elements due to small size, formation of p-pi bonds with itself and with highly electronegative atoms like O or carbon, and non-availability of d orbitals to expand its valence shell. Elements of group 15 show gradation in properties. They react with oxygen, hydrogen, and halogens. They exhibit two important oxidation states of +5 and +3 and +5, but +3 oxidation is favored by heavier elements due to inert pair effect. As we go down the group, heavier elements will prefer lower oxidation state, which is reverse as in case of transition elements, where higher or heavier elements prefer higher oxidation states. Dinitrogen can be prepared in laboratory as well as industrial scale. It forms oxides in various oxidation states as N2O, NO, N2O3, NO2, N2O4, and N2O5. These oxides have resonating structures and have multiple bonds. Ammonia can be prepared by a large scale by Haber's process. HNO3 is an important industrial chemical. It is a strong monobasic acid and is a powerful oxidizing agent. Metals and non-metals react with HNO3 under different conditions to give nitrogen monoxide and nitrogen dioxide. Phosphorus exists as P4 in elemental form. It has allotropic forms which are red, black, and white. It forms hydride pH3, phosphine, which is highly poisonous gas. It forms two types of halides of PX3 and PX5. PCl3 is prepared by the reaction of white phosphorus with dry chlorine, and this is the same for PCl5 as well, but just in excess. And it can also be prepared by thionyl chloride. Phosphorus forms a number of oxoacids depending upon the number of POH groups. Their basicity varies. Basicity is the number of hydrogen atoms it can donate and not the alkaline or acidic nature. Basicity is a new concept, which is the number of hydrogen atoms or protons the acid can donate. The higher the basicity, the higher the acidity. The oxoacid which have pH bonds are good reducing agents. The group 16 elements have general electronegative configuration of NS2 and P4. They show maximum oxidation state of +6. Gradation in physical and chemical properties is observed in group 16 elements. In laboratory, dioxidation is prepared by heating of KClO3 in presence of magnesium oxide. It forms a number of oxides with metals. Allotropic form of oxygen is O3, which is a highly oxidizing agent. Sulfur forms a number of allotropes. Of these, alpha and beta forms, which are yellow rhombic sulfur and monoclinic sulfur, alpha and beta, are the most important. Sulfur combines with oxygen to give oxygen, such as sulfur dioxide, sulfur trioxide. Sulfur dioxide is prepared by the direct union of sulfur and oxygen. Sulfur dioxide is used in the manufacture of H2SO4, where sulfur dioxide in the presence of vanadium pentaoxide, divanadium pentaoxide V2O5 used as a catalyst will react with oxygen to give SO3. This SO3 is then again dissolved in H2SO4 to give oleum, which is the final step in the contact process, which is a name of preparation of H2SO4. Sulfur forms a number of oxoacids. Amongst them, the most important is H2SO4. It is prepared by the contact process. As I said before, it is dehydrating and oxidizing agent. It is used in the manufacture of several compounds. Group 17 of the periodic table consists of the following elements: fluorine, chlorine, bromine, iodine, and these elements and astatine. These elements are extremely reactive, and as such they are found in the combined state only. The common oxidation state of these elements are -1. However, higher oxidation state can be +7 as well. Fluorine cannot show other oxidation state and -1, and fluorine is the most electronegative element and it lacks d orbitals. Because of such a reason, it can only show -1 oxidation state, but remaining elements can show all kinds of oxidation states. They show regular gradation in physical and chemical properties. They can form oxides, hydrogen halides, interhalogen compounds, and oxoacids. Chlorine is conveniently obtained by the reaction of HCl with potassium permanganate. HCl is prepared by heating of NaCl with concentrated H2SO4. Halogens combine with one another to form interhalogen compounds of type X dash, where the X dash is smaller and more electronegative compared to the larger compound, where X dash is lighter than X. A number of oxo acids of halogen are known. In the structures of these oxo acids, halogen in the central atom, which is bonded in each case with OH bond as XOH, in some cases X double bond O bonds are also found. Group 18 of the periodic table consists of noble gases. They have ns2 and p6 valence shell electronic configuration, except helium, which has 1s2. All these gases except radon occur in atmosphere. Radon is obtained as a decay product of radium 226 radium. Due to complete octet of outermost shell, they have less tendency to form compounds. They show one of the highest positive electron gain enthalpy. The best characterized compounds are those of xenon with fluorine and oxygen only under certain conditions. These gases have several uses. Argon is used to provide inert atmosphere. Helium is used in filling balloons for meteorological observation. Neon is used in discharge tubes and fluorescent bulbs. That is the first revision of first revision of p block elements with via NCERT is completed. Okay, then see you in the next video.